We are going to do a talk through of the extra practice problems. Problem one is a solution prep problem. Part A is preparing a solution from a solid. You're trying to make 50 milliliters of 0.50 molar sodium hydroxide solution. You're given a 2.5 kilogram bottle of this solid. Chances are you're not going to use all of the 2.5 kilogram bottle. In fact, you're going to use very little of it. You're trying to figure out amount of grams because that's how we're going to weigh this solid. It takes a lot of time to count the particles, especially when you can't see them. That's really an impossibility. So 50 milliliters is 0.0500 liters times 0.50 moles per liter, which is the molarity, and then times 40.0 grams per mole, which is the molar mass of NaOH. That leaves you with 1 gram. That is not your final answer. You still have to tell how to prepare the solution. So to do that, say put 1.0 grams solid NaOH crystals or flakes or whatever that solid is in a container and add enough water so total volume of solution is 50 milliliters. Notice you're not adding 50 milliliters of water, but enough water so that the total is 50 milliliters, and then mix it, of course. The other main way to prepare a solution is through a dilution of a more concentrated solution. So you got a 1 liter bottle of 3.0 molar sodium hydroxide, and you're asked to prepare 50 milliliters of 0.50 molar sodium hydroxide. So one thing is, it looks like I got a volume here, a molarity here, a volume here, and a molarity here. Don't worry about this 1.0 liter bottles. You're not going to use all of it. Kind of like ketchup, you don't necessarily use the whole bottle, just you use what you need from there. So I think we define in this case V1 we don't know, and M1 is a 3.0 molar, and then the V2 and the M2 are what's given up here, the 50 milliliters and the 0.50 molar. Ultimately, we solve for V1 using the formula V1M1 equals V2M2. V1 equals V2M2 over M1, and we get 50 times 0.5 over 3, which gives me 8.3 milliliters. Let's see if that makes sense. If I have 8.3 milliliters of the 3 molar, and then I dilute it down by adding water, I'm going to end up with a lower molarity because I added a bunch of water to get up to 50. So what's the answer for the solution prep part? It is put 8.3 milliliters of 3 molar NaOH in a container and add enough water so that the total volume of the solution is 50 milliliters, and then you'd want to mix that. Problem number 2, I'm just going to slide this up here so we can see it a little bit better. And let's see, this problem has, and let's get back here so we can see this whole thing. I think that looks okay. So this problem is we got 60 milliliters of 0.18 molar NaCl and 90 milliliters of 0.210 molar MgCl2 and water. So 3 things are mixed, 1 of them water, 2 of them these other solutions. Now look, NaCl and MgCl2 will not react with each other because they have both, there's not going to be a precipitate in this case. So really you just have a bunch of ions of NaCl floating around and a bunch more ions from MgCl2 floating around, then you have more water in there as well. So let's look at the NaCl first. You have the milliliters and the molarity, so you can multiply those together to get to the moles of NaCl. Because NaCl breaks up into in a 1-to-1 ratio, like a single decker ice cream cone, you get, if you have 0.010 or 0.0108 moles of NaCl, you have 0.0108 moles of Na plus, 0.0108 moles of Cl minus. Okay, I'm going to do the same thing with MgCl2. Liters times moles per liter, or molarity, gives me 0.0189 moles of MgCl2. which gives me the same moles of Mg plus 2, but double the moles of Cl minus because of the 2-to-1 ratio. It is like the double-decker ice cream treat, and notice for every 1 MgCl2, you got 2 Cls, so that's why I doubled it right there. So I really only have 3 ions here. I have Na, I have Cl, I have Mg, and then I have more Cl. So if I'm looking at the Na, I'd take my total moles from here, 0.0108, divide it by the total liters in the solution, which is the 60, the 90, and then the 50 of water, which is 200 milliliters or 0.200 liters. And I get 0.0540 molar. With the Mg, I do the same thing. I take the 0.0189 divided by 0.200, get 0.0945. And then the Cl, there are 2 sources. There's the 0.0108 from the Cl minus, and there's 2 times the 0.0189 from the Cl, from the MgCl2, and I add both of those moles together, divide by total liters, and that gives me the molarity of the Cl minus, which is 0.243 molar. Our last problem is the mega problem from the back, and we'll take a look at that. And I'll just get this going together here. The first thing you do is want to write out a balanced equation. Typically, I'm not too worried about the ionic equation. You know how it works, but a balanced molecular equation is the start when you get a problem like this. Let's see if we can find a good spot to launch in on this. Let's try this right here. Okay, I think we got a good place, starting point right here. All right, so I write the equation. Silver nitrate, aluminum chloride, silver chloride, and aluminum nitrate. I balance that equation. Next thing I'm going to do is I'm going to find, I know liters in molarity of the silver nitrate, I know liters in molarity of aluminum chloride. Because I know both reactants, right away I'm thinking it's an excess limiting reactant problem. Liters times molarity gives me moles of AgNO3. Liters times molarity gives me moles of AlCl3. So I got 0.72 moles of silver nitrate, 0.20 moles of aluminum chloride. Just because this is bigger doesn't mean it's the excess. It's supposed to be 3 times bigger, but it's more than 3 times bigger, so the silver nitrate's in excess. Or you could take 0.72 divided by 3. You take 0.20 divided by 1, and the smaller number is this one. So aluminum chloride is the limiting reactant. Silver nitrate is in excess. All the limiting reactant reacts. So 0.20 is this, reacts with 0.60 this. Notice the 3-to-1 ratio, leaving me with 0.72 minus 0.60, 0.12 left. If 0.20 of this reacts, 3-to-1 ratio, 0.60 of this is formed, and 0.20 of this is formed over here. So all of a sudden I have my final numbers, 0.12 here, nothing left here, 0.60 here, 0.20 here. Looking at your solubility table, I'm not going to show that here, but silver chloride is the precipitate. We can just take the moles times the molar mass of silver chloride, and that's going to be the mass of the precipitate. The last thing is to find the ions present. Notice we have the spectator ions, aluminum nitrate, so we have aluminum and nitrate, but we also have the excess silver nitrate ions too. So we really got aluminum, nitrate, silver, and more nitrate. So there's 3 ions, and let's take a look at finding the silver first. I take the 0.12 moles, divide it by the total liters in solution, which is this 800 plus 400, which gives 1,200 milliliters or 1.2 liters, and I get 0.10 molar. With the aluminum, I do the same type of thing, except I start with a 0.20, divide that by 1.20, and get 0.17 molar. And now with the nitrate, I have a couple sources of it. I have 0.12 from over here, and I have 0.20 from here, except it's like a triple-decker cone. It's a 3-to-1 ratio, so I got to take 3 times 0.20 here, and ultimately that 3 times 0.20 is 0.60 plus 0.12 gives me 0.72. Divide that by the total liters, and I get 0.60 molar right here. So just a quick review on this problem. Balance your equation. Take liters times molarity to get to moles here, liters times molarity to get to moles here. Figure out what's excess, figure out what's limiting. The limiting reactant will dictate the amounts of product. The limiting reactant will figure out how much of this is used, how much is left over, figure out any precipitate. And then the last thing is look at what ions are still there. It's the silver nitrate, it's the aluminum nitrate, but this is gone, and then this is all solid and part of the bottom, so we didn't have to worry about that.